Hello and welcome to our lesson on evaluating scatterplots, or finding ways to use information given to predict values. We can find values for x when we're given y, or for y when we're given the x. If you think about what a function is, basically it takes an input. In this case, if we get some number, we can find the output. And so worth writing down, f of x equals y. That means we put in an x and we get out a y. The way to think about it is we have an input and an output of a function. Likewise, in order to find x, we're going to be given a value that was produced and have to try to figure out what might have gone in for that value. So what value would get us a certain output? What's the output for a given input? So these number signs represent we know the number. The y here, or the question mark here, or the x, that represents what we're trying to find, okay? So how many calories are in the smoothie that contains 56 grams of sugar? Well, 56 grams of sugar, that's our input. So we're given 56, and the output is going to be how our body converts that to calories and uses it up. So we find 56, somewhere in between 54 and 58. It looks like from the data, 270 would be pretty accurate. Likewise, how many grams of sugar are in the smoothie that contains 320 calories? So we have the output, we're going to try to find the input. So we outputted, or we knew an output, and what was the input that got us that? Get that clear in your mind. What tends to happen to the number of calories as the number of grams of sugar increases? So this gets back to what the correlation is. As x increases, we always say as x increases, in this case, y looks like it increases. So what tends to happen? Calories, so the calories increase, and we call that a positive correlation. All right, so let's look at some examples to try to look at how we get inputs and find the output, or outputs find the input. This is related to some function notation that we just showed. For each graph or table, evaluate and write the function notation, then explain the meaning of the numbers for each. So the table lists approximate travel times and distance. And just to take a quick moment, again, as x increases, and you might even ask yourself, how do I know which is the independent or dependent variable? Typically, the independent variable is the left column, the dependent's the right. But you can ask yourself, does the time depend on the distance, or does the distance depend on how long we've been traveling? So we're going to work with, this is our x, or input, and this is our y, or output. Independent, dependent. What is the meaning of 6, 355? Well, the meaning is when you travel for 6 hours, you end up a distance of 355 miles from home. That's going to be important. This isn't trivial here. Being able to find numbers is obviously part of math, but interpreting our information is also very important. So you're going to want to make these connections and challenge yourself and ask in class. So here we go, f of 4, that means our input, our time, produced what? 207 miles of travel, okay? So 207. This is the function notation part of it. F of 4 equals 207. This is the meaning part of it. Both are important. Likewise, how long will it take for us to get this far away? So we find 123 on the output and work backwards to find that it was a 2 that got us 123 miles. And it isn't asked here, but a good way of saying that, this one said after 4 hours you've traveled 207 miles. For this one, you could say, to travel 123 miles, it will take 2 hours. Just flip it around, but it's an important distinction. Is there a positive, negative correlation or none? We're assuming there is, obviously. What does it mean in the context of the problem? So look at this. As x increases, what do you notice about y? It has a positive correlation, and as time increases, the distance also increases. That's what a positive correlation would imply in the context of the problem. Continuing with two more problems, and then you'll have some homework. Use the table, which shows the number of species added to the list of endangered and threatened species in the U.S. So you can see X is increasing. The year is independent. How many species that are endangered depends on where we're at in our years. So how many species were added to the list in 2001? Well, we find 2001 and we go up. So let's see, there's 2001. We did find that 10 species were added to the list. What year were 39 species added? So now we're looking on our output, 39, and we're going to say, so put 39 there. We're trying to find this number that gets us to 39, and we would say 2000 was the year. Predict what would happen in 95, and this is, there's very mathematical, technical ways of finding a line that fits this, we say, and then can be used to predict. That's kind of why we like this stuff, is to predict what's happening for future values. So I know that 95 is before 96, obviously, and if it's going down, it's got a negative correlation, then it must have been up higher, or at least we can predict that it was higher in 95. So looking for a number, I'm just going to say 96. You could say there's a few right answers. Clearly, it can't be lower than 90. You know, you could even argue maybe we had the same amount, but it's unlikely that there were fewer in 95, but the trend has decreasing numbers. Likewise, is there a positive or negative correlation, and what does it mean? Take a look at this. We would say that it has a negative correlation because as X is increasing, Y is decreasing. And that means as the years increases, or we go out in time, the number of species that are endangered is decreasing. All right. Our last example. See if you can do this without looking at the rest of the video, and then see how you did. So you can hit pause. All right, so f of 30, that's the way we say this. F parentheses 30 is f of 30. We're going to find 30 on the input and read that as a 20. When you sit in the 30th row, the ticket costs $20. I should have taken a moment. This is a graph of concert ticket costs related to what row you sit in, and hopefully it's intuitive. The closer you are to the front, up to the stage there, the closer you are, the more you spend. The further back you get, the less you pay. Looking at f of 5, so here, if you're going to be in the 5th row, you're spending, let's say, $68. So the way you'd say that is, when you sit in the 5th row, the tickets cost roughly $68. Find X when f of X equals 30. So we have the output to be $30, so that's dollars. We estimate the row to be, well, somewhere between 20 and 25. There's no halves in there, so I'm just going to say 22nd row, row 22. Okay. Likewise, for $40, they look like they might put you in maybe the 20th. I'm going to say the 19th row. So row 19. And does that make sense? When you're sitting closer, the 19th row, you're paying more. When you're sitting further back, you're paying a little bit less. Is there a positive or negative correlation? What does it mean in the context of the problem? See if you can take a guess at what you think I'm going to say. It looks pretty similar to that previous problem. I'd say it has a negative correlation as the rows from the front increases, so you get further away, the ticket price also decreases, I didn't say also. Okay, we'd also call that an inverse relationship. but that's what a negative correlation would be. All right, you should be good to go. Your CYUs, see you in class.